Hi everybody. Welcome to week 5 of Forensic Science. I hope you guys are enjoying the class. I'm kind of delighted. I'm hearing from several of you guys telling me how much you enjoy this class. And we're kind of learning this together. I mean, I know all this material, but learning it from the perspective of forensic science is actually kind of cool to me. And this week is no exception because we're going to be talking this week about chemical analysis. And we're going to be doing some chemistry, and I love chemistry, and so I hope you guys are going to dig in because it's mostly chemistry this week, but I think we make it pretty easy for you. If you already had chemistry, you're going to remember a lot of this. If you haven't had chemistry, okay, you might want to pay very, very close attention. We're going to start out here in the first page of Forensic Science in Schoology. I want you to notice that I've put all the August stuff in a calendar, or in a folder, and so the August calendar is in there somewhere, the videos are in there, and the notebook check number 1 Dropbox is in there. If you haven't given me your notebook for the first, I think it's 4 modules, maybe 3, I'm not sure, then you need to get that done and get it put in there because this is currently a 0 in the grade book. Alright, actually I may not have put that in yet, but I'm about to put these in. I'm about to grade these like today, which for me is Monday the 14th. Also, here's the calendar, and this is the September calendar. Of course, when it runs out, we're going to put all this stuff into a September folder, and there'll be the October calendar. You guys can figure out how this goes. And this is the instructions for last week. The instructions for this week will be right under it. I'm going to go ahead and click on the calendar, and it should take us to this page. Quick reminder, look over here in the right-hand corner while this is loading. I like to push this button when I'm looking at this because it just makes it where I can see it better. This was week 3. This was week 4 last week. Last week we talked about collecting physical evidence, and so yeah, and there's where it said scan and it's submit notebooks. You're supposed to do it last week. This week, just a point of fact, technically Monday, September 14th is a teacher professional development day, and there's no class for you. Now, that doesn't mean you can't do class, so if it's Monday, September 14th, which is for me today, then you can work on this all you want. I'm going to open all this up as soon as I get through with this if I haven't already opened it up. And you know what, I'm going to do that now. Hold on. Yep, so now it's open. Okay, I'm back. I want to carry you through the tutorial. This guy here, I want to show you the guided notes real fast, and then I wanted to show you this picture of the periodic table of the elements and tell you what's going on. So this week is technically only 4 days, but it's 4 pretty solid days. And don't forget these areas over here, these guys right here. Well, I can't highlight it, but these things right here, because I know that they're enrichment, but I would really encourage you to watch those, especially, well, watch them both, because we're going to talk about the Lassigne's test briefly, and I want you to get a better idea of what it is. But even on this one, if you are, just watch it. Just watch the video. Watch how they do it. If there's words in there you don't understand, that's fine. I just want you to see what the process is. Okay. And then this one under here, the real science of forensics. That's a well done video, and they show you, they kind of carry you through this process of a particular crime scene and what they do. And they talk about what like stuff you see on TV. They talk about, oh no, that actually works, versus, oh no, that's stupid. So I really enjoy that video. I'm going to carry you through the tutorial. Actually, first thing I'm going to show you the guided notes. That's right here. Then I'm going to carry you through the tutorial. Now, even though it's week 5, I still don't think I've got everybody totally understanding this. You are to print these out. Okay, there are 5 pages. You are to print these out. You will notice that a lot of it is already there for you. Okay, but whenever there's a blank space like right there, just fill it in. But you need to read all of it. Another thing is that in these notes, I put in some color because I wanted you to kind of see that, that they're kind of separate. Like here, 2H2 means this is 2 hydrogen atoms bonded together to give us something called H2, and then there's 2 of those. So quick question right here, how many hydrogen atoms are there? If you said 2, you got to think again, because there's 2 hydrogen atoms here bonded together, and then I have 2 of those, so it's a grand total of how many hydrogen atoms? 4. How many oxygen atoms are here? That's right, 2. Now, when we do chemical reactions, the same number on the left has to be on the right. So, even though I'm taking these hydrogens and oxygens, sticking them together, and I get 2 water molecules, inside of those 2 water molecules, how many oxygens are there? 2. How many hydrogens are there? 4. Okay? It's called balancing equations. It's actually called stoichiometry, but that's another day. I color code these to some degree because down here it's even, this is coming straight out of the book. I mean, straight out of the notes, straight out of the tutorial. But in here, I want you to see the color of it. Okay. For example, this is called a combination or synthesis reaction. That's when we take an A atom and a B atom and stick them together to get an AB atom, just like what we just showed you here. This is, I'm sorry, an AB molecule. So if I take 2 hydrogen atoms, that's the A, and I'm sorry, 2 hydrogen molecules, that's the A, and 2 oxygen atoms, that's a B, stick them together, you get the AB stuck together. So they're kind of color coordinated, like these H's here correspond with these A's. I hope that helps you. When you print this out, it doesn't have to be in color, but you may want to highlight them if you don't print it out in color. But right here in the end, yeah, there's a little bit of writing to do, but for the most part, I've done all the work for you. So print these out, fill them out, read them, okay, but complete them as you go through here. So real quickly, we're going to go through this. This is chemical analysis of evidence, and the objective is that you will describe the methods used to analyze the chemical composition of evidence recovered from the crime scene. And I emphasize chemical because next week we're going to talk about using light to look at crime scenes. So we're kind of looking at ways in which we can look at crime scenes, and this week we're looking at chemistry. Now I jumped way ahead, so pause this if you need to, but the first thing we're going to talk about is the physical and chemical properties of matter. What's that got to do with forensics? Well, it's got a lot to do with forensics, because forensics is the study of crime scenes, and guess what crime scenes are made of? Physical matter, chemicals. Okay, so we need to study them, and here it talks about when we look at physical properties, what are we looking at? What is a physical property? That's what this paragraph talks about. This paragraph talks about what chemical properties are. Physical properties are things that you can change it, but the underlying stuff such as water doesn't change. For example, we can boil water, we can freeze water, we can turn it into steam, we can do all kinds of things, but it's still water. So that's a physical change. But chemical changes are things like toxicity, flammability, combustibility. We can take, for example, water, and we can pass electricity through it, and it actually rather easily rips it apart, and it turns it into hydrogen and oxygen gas. That's a chemical change. So physical changes are when we don't actually change the molecules that make it up, but we just change what it looks like, color, odor, density. Chemical changes are when we actually change the chemicals, or at least how the chemicals are bonded together. Now, when we talk about chemicals, one of the things we need to talk about here is the periodic table of the elements. And yes, you need to learn this, and I actually give you a pretty good video here, Crash Course Chemistry, the periodic table. I don't know how you guys feel about Hank, but I think Hank is a genius, and this is one of his shorter ones. And when you watch Hank, he talks very fast. You may have to pause it and just go, give me just a minute, Hank. But this really gives you a great explanation for why the periodic table is the way it is, and I think you guys should be watching that. Here is the periodic table. I'm actually going to zoom in a little bit. I tried to pick one that showed you all the important parts without it being too difficult to read. Let's pick a square. We'll just start with hydrogen. Everybody starts there. Hydrogen is in this column. We call that a family, I think. Crap, I forgot. But anyway, that column, everything in this column shares a somewhat similar set of characteristics, and that video with Hank shows you this. Okay. Also, there's the number, the chemical symbol, and in this case it's H for hydrogen, not to be confused with HE for helium. I think those are the only two that aren't in there, right? And it's actually kind of a ton of fun to go through here and create words using these. And so yeah, you can create dirty words too, just don't tell me. But also in this box there's a couple of things. This is called the atomic weight. This is the average weight of each chemical, or of each atom, and it should be reasonably close to this number sometimes, but this number is not the same as this number hardly ever, because of the fact that all atoms have something called isomers and isotopes, and isotopes throw these numbers off. So this is the average weight of hydrogen, and that's just a whole nother day. This is the atomic mass. You just totally just forget it. You'll learn it one other day in chemistry. But one thing that's interesting is the atomic number. The atomic number refers to how many protons there are in the nucleus of this atom. Now that's important that you understand that. It refers to the number of protons, not electrons. Okay, how many protons does where's plutonium? I think that's plutonium. Plutonium has how many protons, everybody? That's right, 94. Okay, take a look at oxygen. It has 8. Carbon has 6. These are important because they tell you how many electrons there are. Wait, what? Why don't we just count the electrons? Because the number of electrons can change, but the number of protons doesn't change. So I'm just trying to do a real quick dirty chemistry review here. The number of protons always stays the same. If you have 25 proteins, then you have Mn, which I think is manganese, right? There's no other way around that. The number of electrons can change, the number of neutrons can change. That's where we get these isotopes. That's another story. But if you have 25 protons, then you got manganese, and that is that. So we count how many protons there are to determine what atom we're looking at. Okay, now because protons have a positive charge, we even that out with a negative charge, and the things that make it negative are electrons. So for most cases, until you learn how the protons move or the electrons move around, this number also tells you the number of electrons. If you could isolate in a vacuum and have nothing else in there, one hydrogen, okay, it would have one proton. The problem is they don't exist that way. They can't. They bond. They're highly reactive, except for this row right here. They're highly reactive. So we never just find an oxygen atom laying around by itself. All right, nature doesn't let that happen. So that's why we need to know how many numbers, or what these numbers are, because they tell us how they'll stick together. And that's a whole other thing with chemistry I'm not going to teach you today, but this is called the atomic number, and it's very important. So I want you to print this out, and I want you to put it inside of your notebook. Maybe even make some notes here after you watch Hank in his video, because it tells you some really important stuff about how it was discovered, and that really helps you to understand why it's shaped the way it is. And also, here's something interesting. This whole set of squares right here is supposed to fit right in these two boxes. This whole row here, called the lanthanide series, is supposed to go right here in this box. But if we did, and I think, yeah, these would stay there, but this right here, if we like cut it with a pair of scissors and stretched it way out, you could put these in there, but then it would be very wide, and that's not easy to put onto a poster or a piece of paper. So they pull these out, they kind of crunch it together, and they put these down here. Okay, so that's why they're here. This is not the biggest one, and as you'll notice, as we go from the top left to the bottom right, they're getting bigger, the numbers are getting larger. But this one right here, all the way at the bottom right, that's not the biggest one, because technically it's stuck in there somewhere. This one, UUO, which has a name now, I forget what it is the biggest atom that we know of. It has 118 protons, and it's highly radioactive, and it really doesn't exist by itself in nature very much. We have to make it inside of a huge proton collider, but that's another story. Okay, all right, one day you're going to learn more about this if you haven't already, but we're going to go back to this. So the periodic table of the elements, I just explained all that to you. Hank does a great job too, but go through this and take the notes. And this page is just more of it. It talks about each set of elements in these groups. These numbered things up here are the groups, and it just talks about them. Hank also talks about them, so I'm really hoping you go watch Hank. I don't want you to think you have to know all this stuff, but I want you to get a casual understanding of it, to understand that everything in this green square right here, they are similar in terms of their characteristics. Everything in this purple square, okay? And so it's important that you understand that about the periodic table. And the guy that came up with it, Mendeleev, was absolutely brilliant. So then we're gonna start talking about physical properties. Physical properties include things such as weight, length, temperature, color, smell. These are all chemical properties, and so we talk about how we measure those. You're very aware of this, but I do want you to write this down. A foot is exactly 30 centimeters, although not exactly. It's close to 30 centimeters. A yard is close to 90 centimeters. A pound is 450 grams. A fluid ounce is 9.5 milliliters. You need to know these things because here in the United States we don't use the metric system, and the metric system is very useful and everywhere in the world except for us, one little bitty podunk country in Africa and a small country in Asia called Bhutan. Everybody else in the world uses the metric system. It is a universal system, and I very much wish that we used it here. I love my miles. I love my yards and pounds. I don't want to buy a liter of ice cream. I want to buy a quart of ice cream. But I also know that in terms of the math and in terms of science, the metric system is far more useful. And so whenever we deal with science and deal with math, typically we're going to be dealing with the metric system. Alright, jumped ahead a little bit. Now we're talking about types of chemical reactions. Chemical reactions are when we take two sets of chemicals and mix them together. These chemicals can be in the form of compounds. What we mix together can end up being in the form of something called a compound or a mixture, just depending on how it's mixed together. You do need to know the difference in the two, so make sure that you're reading this. But remember, chemical reactions are when you take two different sets of chemicals and combine them in some way. It either requires energy to put it together, or When you put it together, energy is released. That's very important to know. And here's where we start talking about all those different kinds. Now, the video that I left for you, I think, has 5 different kinds. I'm not sure, but we're going to be talking about 4 different kinds. The first one is called a combination or a synthesis reaction. Very simple. Combination means to combine, just like synthesis means to put together. And look at what we're doing. We're taking an A and a B, and we're putting it together to make AB. Such as, I've already shown you this, two hydrogen molecules and 2 oxygen atoms go together to give me 2 water molecules. Okay, that's a combination reaction. Very simple, straightforward, happens all the time. A decomposition reaction is just the opposite. So start thinking of these two as the opposite, and they give you the opposite chemical reaction to show you that these things do go backwards and forwards. If I take 2 waters and kind of shred them apart, I can get 2 hydrogen molecules, which is really 4 hydrogen atoms, plus 2 oxygen molecules. That's what we breathe right there, by the way. And as a result, I have decomposed this molecule as opposed to composed it like I did up here. Very simple. This is like, think about it, almost like Legos. This is like putting it together and tearing it apart. That's combination or synthesis reaction at the top and decomposition at the bottom. And then the last 2 are replacement reactions. And basically, and again, if you really want to think of these as Legos, that always helps me out. Each of these little letters, they represent atoms, but the atoms are like Legos. So I have 2 Legos stuck together here, a B and a C, okay? And then I have an A out here all by itself. Now this reaction, they didn't write it correct, okay? So in your notes, it should say right here, it should say plus B. And basically, I'm pulling the B Lego off of here, putting it out to the side, and I'm putting the A Lego on there. That's a single replacement. I just swapped the B out for the A. And you can see the reaction here. I've got something called hydrogen chloride, which is an acid here, right? And then I got zinc on the outside. Well, if you mix them together, the hydrogens pop off and the zinc goes on, and I just replaced it. Just think of it like Legos, okay? This is a single replacement, which means I'm swapping out one, but this is a double replacement, which means that we're kind of taking, everybody's swapping here. So I take this B off of here and put it over here, and I take the C off here and put it over here, and I'll get AC plus BD. And here is a very common reaction. Hydrogen chloride plus sodium hydroxide gives me, believe it or not, salt and water. So kind of a weird little reaction there. But the hydrogen came off of here and attached to the OHs, and the sodium came off of here and attached to the Cl, and the oxygen. What I said, the oxygen came off here and attached. Can't even talk. The sodium came off here and attached to the Cl, leaving an oxygen and a hydrogen over here, plus another hydrogen over here, so I get water. But it's just easy. It's a double replacement. Again, if you think Legos, you got this covered. So how does all this apply to a crime scene? Well, quite often crime scenes are covered with things that can benefit from chemical analysis. We can learn a lot by looking at the substance that's on a knife, for example, or looking at the whatever the stain is on the carpet, or whatever the splatter is. And when we look at things, we need to understand the chemistry of it. So we talk about things like the identification of it, which is it establishes the physical and the chemical characteristics. We then can compare those to see if they have a common origin, such as this chemical came from, this chemical has a certain trace signature to it, so we know that it was made by this company. I know that sounds like something straight out of the movies, but it's actually true. And I mean, we can also compare the DNA in blood to existing known DNA samples, and that's happens all the time. That's why we study DNA. We can do things like determine what kinds of carbon and hydrogen mixtures there are in there. The presence of carbon and hydrogen usually tells us something. It tells us that it's a living substance usually. How do we do that? We perform a test, and it's not pretty. It's actually kind of burns things. It probably smells bad, but you can then tell, was there carbon there? Was there hydrogen there? And then it tells the investigator a lot. One way to do that is with the lasagna test, because I think it's pronounced lasagnes, but I just say lasagna. But the test for nitrogen, sulfur, halogens, and so at this point we've already tested for carbon, hydrogen, nitrogen, sulfur, halogens, and what we can do is we can then go back and say to somebody after we've done all these tests, there was this there and this there in this ratio, and this tells us something. So that's it. I mean, I know I kind of rushed through it, but I got like 27 seconds left before I hit 20 minutes, and I always try to be on at 20. So what we're doing is basically in this tutorial, we're talking about what are physical and chemical properties, how does the periodic table work, and show us about how chemical reactions work. And then we take all that knowledge and we apply it to a crime scene by examining what kind of chemicals are there. And I just gave you a quick and dirty. I mean, there's a whole lot more to study. in terms of chemicals. And I just hit 20, so give me another 30 seconds. But when we go to a crime scene, we can study DNA. That's a chemical. We can study, I don't know, motor oil at the scene can tell us something, because if we know that there's this kind of motor oil at the crime scene and the same kind of motor oil is in that guy's truck, that means there's a good chance that truck was here. So we have to do all these tests to learn that. And as a result, it really helps prosecutors make a case. Alright, I'm done. Have a good week, and I will see you next week. Text me, email me, Zoom with me, call me, whatever you need. Goodbye.